slides in order to keep with the timetable. So let's begin. There's no sound from the microphone yet. I hope that sound comes during the next few minutes because I have some audio examples that I want to play. Well, the title of this presentation is Probabilistic Harmonization with Fixed Intermediate Chord Constraints. It's a work within the context of the co-invent project, an FP7 project from the European Research Council, which discusses the creativity in computers and our part, the part of the cognitive and computational creativity group from the Aristotle University of Thessaloniki, is to produce a system that creates melodic harmonizations in an intelligent and creative way. What is melodic harmonization? It's the assignment of harmonic material on the notes of a given melody, which means that we have a given melody and we have to import some chords which harmonize the melody in a good way. Well, and the methodologies that have been proposed towards this direction is the utilization of human expert knowledge encoded in the forms of rules, which means that there are some rules that say which chords go where and which chords can harmonize which note of the melody, with generic algorithms which use fitness functions that incorporate something like rules, and some probabilistic or statistical learning techniques, which is the kind of algorithms that the present algorithm uses. The base of this algorithm, the constraint hidden Markov model, is the hidden Markov model, the typical hidden Markov model, which, according to the literature, presents some local harmonic coherence, which means that one after the other, the chords have some coherence, and the harmonies that are produced do reflect the idiom that the system has been trained on. Additionally, the constraint hidden Markov model allows global control of harmonic movement, which means that while the typical hidden Markov model just adjusts the chords from one chord to the other, the chord progressions, the constraint hidden Markov model allows to import some chord constraints at the full extent of the melody, so you can have a larger scale control. And it also allows some potentially blending mechanisms. The blending mechanisms are some mechanisms introduced within the, not introduced, utilized for the co-invent project that I was referring to previously. We'll have a talk about that in the end. So let's, well, our motivation to use to develop such a technique is we initially wanted to use a statistical learning and probabilistic technique for melodic harmonization. The hidden Markov models are well suited for this task, according to a great literature over this issue. Additionally, some chords play an important role, which means that, for example, cadences. We want the cadences to be good cadences. With the hidden Markov models, we cannot have such a large-scale control of the melody. So, with the constraint hidden Markov model that we propose, it is feasible to import good cadences and let the hidden Markov model produce a harmonization that sticks to this cadence. And additionally, intermediate chord constraints, as we said previously, allows some larger scale control of the harmony, which means that we can import a cadence that we like, an intermediate cadence that we like, and let the system probabilistically produce a harmonization over a melody. So, we need a methodology that allows to import checkpoint chords, either automatically, which is a huge matter of discussion, but not discussed in this presentation. We can have a discussion at the end, or manually. This methodology can learn from the statistics from a given idiom, and then fill the remaining chords, which means that we import checkpoints, we learn, and then fill in the remaining chords. And also, this methodology offers some expandability to additional harmonic concepts, which is another huge matter of discussion. I hope that we can get through some rough description at the end. Now, what is the big idea? We have a melody, M1, M2. All these are melody notes. Okay, suppose that we want to harmonize each melody of the note, like a baccarat, for example, something like that. But we have some constraints, I1, I2, and I3. These I1, I2, and I3 are some chords that we are positively sure that need to be there. For example, M1 needs to be harmonized with I1. Melody note M5 needs to be harmonized with I2, and M8 with I3. So we say, here we are, these are the constraints. That's filling the remaining chords, which are the C chords at the end. So what do? At the bottom we see the CHMM, which is the constraint HMM. This is the methodology that has been proposed. But this wide context has been split into two, for example, here, with a boundary constraint hidden Markov model. This is the BCHMM, and another one boundary constraint hidden Markov model on both sides, which are both constrained by two boundary constraints. This is why the boundary constraint hidden Markov model, BCHMM. So, two boundary constraints here, two boundary constraints there. They all create a constraint hidden Markov model. This can be filled in with multiple successive boundary constraints. For example, if we have 4 intermediate constraints, we can split it into 3 boundary constraint problems, which is what we're talking about. Now, the HMM technical aspects, I think that we can go a little faster around this. So, what probabilities are incorporated into the typical hidden Markov model? The probability for each state to be a beginning chord. This is a probability. Some chords are more probable to be beginning chords than others. The probability for each state to be an ending chord. In fact, I think, correct me if I'm wrong, this was first introduced in the My Song by Microsoft, I think. My Song by Microsoft, which is now, My Song now has another name. It's a product you can buy for Windows phones. So we have some probability for a chord to be a beginning chord, a probability for a chord to be an ending chord, the probability that each state follows another state, that each chord follows another chord. We have a transition, a matrix of probability of transition probabilities, and the probability of a chord to be played while a melody note exists in the melody at the same time. These are the 4 probabilities utilized by the typical hidden Markov model. Now, for the constraint hidden Markov model, we need some square chords to be fixed and not to be arranged by some probabilities. So, we split into successive boundary constraint hidden Markov models, and each boundary constraint model, there's a simple modification. We say that, okay, we need to be sure about the beginning and the ending chord, so what we do? We say that, okay, a fixed probability, 1 for the desired chord, and 0 for all the other chords. And the same for the end. So the Viterbi algorithm from the hidden Markov models is obligated to follow a path that considers only the selected chords for beginning and ending chords for the boundary constraint hidden Markov models. So it's a simple modification of the probability in the beginning and in the ending. Now for the examples, the representation of chords that we incorporated is not the standard, the fixed types that were considered in previous works in the literature. For example, the major, minor, or diminished chords. In the Convent project, we're dealing with idioms that are very strange harmonically, that are not the chords, the pitch class simultaneities that sound do not conform to the major, minor, or diminished, or the Western musical chord namings. So we have developed the general chord type, which is a presentation. I believe the presentation is tomorrow morning for the general chord type, if you're interested. It embodies the information of both the consonant and the dissonant chord part. Each chord is represented in 3 parts, which is the root. For example, as you see there, the 7, The first number is the root. A base, which is a 047, which indicates something like a major. We can think of it. And an extension, which is the 10, which means that this chord indicates the dominant 7th chord. More details tomorrow. We have also trained the constraint Markov model with 30 phrases. The chord node probabilities were these are technical stuff. I guess that we should skip all that since we have 5 minutes more. These are some statistics. I think that in the paper you can find everything you like. Here are the examples. We have a microphone. Έχω ένα μικρόφωνο.
Έχεις πρόκειται καλό δίμηνο.